All right, so we're back here for part 2. Now, at the top here on the back, we're going to write a couple of things down. To be a binary situation, okay, I'm going to leave some space over here. To be a binary situation, what we want to remember, or what we need to check for, is our bins. Okay, so there are 4 conditions for us to be able to use the formula for a binary experiment. Now, the probability of this happening, a binomial distribution, so on the left side here, the probability that x is equal to k, whatever the number of times something's going to happen, is the combination of n objects taken k at a time times p raised to the k times 1 minus p raised to the n minus k. Okay, now we'll come back to this. This is the formula that's on your AP Statistics formula sheet. To be able to use this, though, we need to know that we have a binary distribution. Well, the first, so bins, stands for, first of all, we need to know that the situation is binary. And what that means is that we only have 2 possible outcomes. We have success or we have failure. I means that the events need to be independent. All of the outcomes need to be independent. So independent, and we've talked about this, means knowing that the results of one trial, does not affect the result of another trial. Knowing the results of one trial does not affect the result of another trial. So one event does not affect the next event. That's what independent means. We need to have a fixed number of trials. Fixed, that's my number symbol, of trials. Okay, we call that n. That's the value n. And then S means success. Whoops. S stands for success. We have to have the same probability of success for every trial. Same probability of success for every trial. So in other words, the probabilities don't change. If we flip a coin, the probability of getting heads is always 0.5. That's not going to change. It doesn't matter what happened before because the coin doesn't have a memory. Okay, so whatever I flip on the first, or whatever I get on the first flip does not affect what happens on the next flip. Okay, so these are the 4 things that have to be true for us to be able to talk about a binary distribution and to use this formula. Okay, so again, K is the number of times that we want to succeed. That's the number of successes. N is the number of trials. And then P is the probability of success. So let's look at a couple of examples here. Number 2, we're going to talk about eggs. The proportion of egg cartons with at least 1 cracked egg is 0.13. 9 cartons are on the shelf at Tesco. What is the probability that at most one of them will have at least 1 cracked egg? All right, so we're talking about egg cartons. We can have 2 outcomes, that we have cracked eggs or not cracked eggs. Okay, so that each carton will have at least 1 cracked egg or it will have no cracked eggs. So I'm going to think of this as C plus N. C means that a carton has a cracked egg, at least 1, and N means that none of them are cracked in that carton. Now we're going to take 9 cartons. So we're going to have a fixed number of trials. So that will be my exponent here. It'll be raised to the 9th power. In terms of probabilities, The probability that at least one egg is cracked is 0.13. Well, that means that the probability that no eggs are cracked in a carton would be 1 minus that, which is 0.87. Now, that adds up to 1, and then again it's raised to the 9th power. Now, I haven't used the formula yet. This is just how I'm going to organize it. We want the probability that at most one carton will have at least a cracked egg. So we are looking for the probability of at most one carton with a cracked egg. Now that could be, there's two possibilities. At most one means that or less than. So we could have 0 cracked cartons, or we could have 1 cracked carton. So those are the two probabilities that we need to figure out. What's the probability that no cartons have cracked eggs? What's the probability that 1 carton has at least 1 cracked egg? So if I'm using this formula here, out of 9 cartons, we're going to choose, we want 0 to be cracked. The probability of a carton having at least 1 cracked egg is 0.13. Now that's raised. Again, we want none of them to be cracked, which means we want all 9 cartons to not be cracked. So that's the probability of not cracked raised to the 9th. Okay, plus the probability that we have 1 carton with cracked eggs. Out of 9, 1 of them will have cracked eggs. So that means I'm just going to write 0.13. Raised to the first, because only 1 of them will be cracked. And then 0.87. If 1 carton is cracked, that means the other 8 are not. Okay, so the exponents have to add up to the total number of trials. All right, so now it's a calculator problem. Now I can certainly just type all of this. I can also use the calculator a little bit faster. If I go second and distribution, which is where we go for our normal distribution, PDF, CDF, well, if I go down, I have binomial. Okay, now if I do binomial PDF, that would be for one specific outcome. The number of trials is 9. The probability of a cracked egg. Now that's, in this case, this is our success. This is success and this is failure right here. So success means that at least one egg is cracked in a carton. That is 0.13. The X value is the number of cartons that are cracked. So for here, it would be 0. And that's 0.2855. So 0.2855, and then plus, over here, second distribution, go down, binomial, PDF, 9 trials, the probability that an egg is cracked in a carton is 0.13, that at least 1 egg is cracked in a carton. And now we want 1 carton to have a cracked egg, at least a cracked egg. And calculate 0.3840. So the probability that at most 1 carton has a cracked egg is going to be to add these. So 0.2855 plus 0.3840. And what we get is 0.6695. So equals 0.6695. That is the probability that at most 1 carton has at least a cracked egg. So it's almost a 67% chance. Now I can do this even faster. If I go to binomial CDF, which is cumulative, 9 trials, 0.13 is the probability of a carton having at least 1 cracked egg. Now this time, if I type 1 for the X value, that's going to find 1 carton cracked or less, this or less. And notice that we have the same answer, 0.6695. Okay, actually I should probably say 0.6696 for that. So if I do binomial CDF 9.131, this is the number of trials. This is the probability of success. Now, this means less than or equal to 1 happening. Okay, so that is the answer to number 2. Let's try, let's talk about exams. Number 3. A biology quiz consists of 8 multiple choice questions. 5 must be answered correctly to receive a passing grade. Okay, so that's important. We have multiple choice questions, 8 of them, so that's going to be the n value. That's the number of outcomes. If each question has 5 possible answers, find the probability that the student passes the quiz. Well, we have to assume here. Let's say that they're guessing. So let's say you study for your biology quiz and then realize that you have no idea what's going on. So you're going to have to guess. You have 8 questions. Find the probability that the student passes. Now, passing the quiz means you have to answer at least 5 correctly. 5 must be answered correctly to receive a passing grade. Okay, so we're looking for at least 5 correct. So our 2 possible outcomes for each question is we can be correct or we can be wrong or not correct. Let's go N for not correct. We have 8 trials because we have 8 possible questions. And so what we're looking for, we want the probability that we have at least 5 correct. Well, now that could be 5 correct, that could be 6 correct, that could be 7 correct, that could be 8 correct. Okay, so there's 4 trials, and we'd have to do this 4 times. Okay, now, what's the other possibility? So we can do this individually if we want to. Now, in terms of correct and incorrect, if we're guessing and we have 5 choices, the probability that we're correct is 1 out of 5, which is 0.2. That means the probability that we guess wrong is 0.8. I'm not liking our chances here. I don't like our probabilities. So we can do this 4 times, where if we're using the formula, 8 questions, we're going to get 5 correct. The probability of success is 0.2. Remember, we're getting 5 correct. The probability of failure is 0.8. If 5 questions are right, then 3 are wrong. Plus, now we're going to get 6 correct, 0.2 raised to the 6th. 2 questions wrong, so 2 is the exponent for 0.8, that probability. 7 correct. So now it's 0.2 to the 7th times 0.8 raised to the 1st, that's 1 wrong. And then if we get them all correct, that would be amazing. So out of 8 questions, we get 8 of them right. There's a 20% chance that we guess correctly for all 8. 0.2 to the 8th. Now this is 0.8 to the 0. Okay, now again, we can do these individually and calculate them. You can use binomial PDF if you want, but there's a faster way to do this. The other possibility, at least 5 correct, is the same as 1 minus the probability that we get less than 5 correct answers, or 1 minus the probability at most we get 4 correct. Okay? 1 minus the probability that we get at most 4 answers correct. If we get 0, 1, 2, 3, or 4 answers correct, then we are failing this. Okay? So if we can find that and then subtract it from 100%, subtract it from 1, whatever's left over is the probability that we get at least 5 correct. So if I'm going to use the calculator, I can do binomial CDF, 8 trials, 0.2 is the probability of guessing correctly. Now in this case, we want to calculate for 0, 1, 2, 3, 4. So 4 is the number. It has to be less than or equal to this number. Okay, so I wouldn't put 5 in because then it would include 5 correct as part of this, which we don't want. So, binomial CDF, 8 trials, 0.2, now 4. Now this represents 4 correct answers or less. So the probability is 0.9896. 0.9896. So the probability that we get at most 4 answers correct, now this is if we're guessing, is very high. So the probability that we get 5 or more correct guessing is very low. It's 1 minus that. So if we subtract, we get 0.0104. That is the probability that we guess and we get at least 5 correct answers. So we have a 1% chance of passing if we're randomly guessing. So the moral of the story is we don't want to randomly guess. And that's the end of part 2.